is associated with this matrix? Rotation. Yeah. A is an n by n invertible matrix. How many pivots does it have? N. Good. And what are the homogeneous coordinates for the point 3, 4? 3, 4, 1. Right? Or you could write it vertically. 3, 4, 1. Okay, so 2.3 focused around the invertible matrix theorem. And the invertible matrix theorem really pulls together a lot of the concepts that we learned in chapter 1. So I've just reprinted it here from your book. It says all of the following statements are equivalent. Okay, if A is a square n by n matrix, that's the only time you can use the invertible matrix theorem, is if you have a square matrix. So it says that for a given A, the statements are either all true or all false. So if you're asked anything from this list, right, if you are asked, do the columns of A span Rm, or Rn, sorry, and it's easier to answer, does A have n pivot positions? The answers to those two questions are the same, right? So if you can answer one of these easily, you've answered all of them. So you kind of like sort of pick which one's easiest to answer based on what was asked of you. So let's go through and see if we can like sort of briefly justify why these are all the same. Okay. So A is invertible, right? They told us that A is, so if A is an invertible matrix, the way you find the inverse of A was you augmented A with the identity, right? And you row reduce, and the identity shows up on the left and A inverse shows up on the right, which means that A is row equivalent to the identity matrix. So A can be row reduced to the identity. So that's part B, right? So if A is invertible, that means you can find A inverse by this method, which means that A has to be row equivalent to the identity matrix, which means that A has to have n pivot positions because the identity matrix has a 1 in every diagonal spot. So there's n of those spots. So A has n pivot positions. It means the equation AX equals 0 has only the trivial solution because there is a pivot in every column. Which is the definition of linearly independent. Okay, so check, check. The linear transformation is 1 to 1. That was pivot in every column. Yeah. The equation AX equals B has at least one solution for each B and Rn. That is the definition of onto and spanning Rn. So these three are just equivalent by definition. And they are all true because there would be a pivot in every row. Onto, same thing. There is an n by n matrix C such that C times A equals I. That's just the definition of an inverse. That just says that A inverse exists. And you can do the multiplication in either order. And A transpose is also invertible. We're going to prove this one in our lesson. So it all boils down to being equivalent to the identity matrix. You can answer all of these by the fact that there's a pivot in every row and a pivot in every column. All right, so we have 2 of the 4 matrices can be seen to be singular. That is that they are not invertible. They don't have an inverse by inspection. 1 can be seen to be invertible, meaning it has an inverse. And the 4th is not so easily determined. So what do you think? Can you pick one out that is definitely not invertible? Caitlin. B and C, yeah, because of the rows. This is definitely not going to have a pivot, and neither is this one. They're going to be missing pivots because you can't change the zeros, right? So B and C are going to be missing pivot positions. Not enough pivots. Okay, which matrix definitely has an inverse, and you can tell just by a quick look at it. A, yeah, and it's because it's triangular, right? It's not lower triangular, which is what we're used to seeing, but you can easily make it lower triangular by just swapping rows. Like if you just swap, can they do that? I don't know. But anyway, it's triangular. So A, because it's triangular, it's going to have 3 pivot positions. And then D is not as easy to determine. You can't tell just by looking at it. So we're going to have to row reduce it and make sure it row reduces to the identity. So D, does it row reduce to 1 0 0 0 1 0 0 0 1? You just check on a calculator and it does. So it is invertible. Okay, A is an n by n matrix, so it's square, which means that I can use the invertible matrix theorem if I want. And the transformation T of x equals AX is 1 to 1. What else can you say about that transformation? Everything from the list, yeah. It's on to, because there are only 2 statements about transformations. All the other statements are about the matrix or the columns of the matrix, right? So it's on, it maps onto our n. All right, so the last thing I want to do with you before you try some things on your own is to prove that the last statement is true, that if A is invertible, then so is A transpose, because that one is not as obviously intuitive, I don't think, by just thinking about the fact that A row reduces to the identity. All right, so we're getting into the part of the course we're gonna start writing some little proofs. So we did some proofs in like the first day, but it was all of stuff that we were familiar with. Now we're going to be doing more and more proofs of linear algebra stuff. So a proof, again, is just an argument. Start with what's given, argue, 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 conclude the second part. Conclude that A transpose must be invertible. Okay, so that we're given A is invertible. We need to show, right? We need to prove that A transpose is invertible. All right, so given that A is invertible, that means that all that means is that A inverse exists, right? And I can use a ton of stuff from the invertible matrix theorem because A is invertible, so all those other things are true, right? So I can argue using the invertible matrix theorem, and then I want to conclude that A transpose is invertible, which means that there is an inverse, right? So the definition of A transpose having an inverse is that we're looking that there is some matrix C such that C times A transpose gives me the identity, and that A transpose times C gives me the identity. And that's the definition of an inverse, that when you multiply by it, you get the identity. All right, so I'm going to be using what I'm given, then I'm going to argue, 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 and I want to come up with, I'm going to try to create a matrix C that is the inverse of A transpose. Yeah. Yes. Yeah. Yeah, that's all part of our need to show. All right, so if A inverse exists, I'm going to write it in sentences. Since A is invertible, that means A inverse exists, so I know that A times A inverse gives me the identity. That's the definition of having an inverse. So get this equation here. I can manipulate equations however I want, basically, as long as you do the same thing to both sides. So I'm going to take this equation, I'm going to take the transpose of both sides. Take the transpose of both sides to get, so I have A times A inverse, that's a matrix, and I'm going to take its transpose. It equals the identity transposed. What is the transpose of the identity matrix? If you take each column and make it a row, or each row and make it a column, it's still the identity. Yeah. So I transpose is just I. So I'm just going to say thus, working with that equation, the right side I know is I. And then do you guys remember from the 2.1 where we did all the arithmetic with matrices? Which statement was true about if you have the product and you take a transpose? Do you remember how it works? What? Does it just distribute, or is there was like a weird thing that happened? It like reversed the order. Yeah. So this is A inverse transpose times A transpose. So it doesn't just distribute, you have to reverse the order and transpose each one. All right, so let's remember, done a bunch of algebraic manipulation here. Let's remember what we were looking for. We were looking for a matrix so that when I multiply it by A transpose, I get the identity. I found one, right? I have a matrix here that when I multiply it by A transpose, I get the identity. So that's the inverse of A transpose. This is the C I was looking for. So A transpose is invertible because it has an inverse. There is some matrix that I can multiply by A transpose and I get the identity. So A transpose is invertible because it has an inverse. And I found it.